Welcome back. So, we are talking about renormalization. Let us quickly recap the example. We are talking in phi 4 theory. The two parameters are m and lambda. H bar is taken as 10 to the power minus 2. The expression for the 2 point and the 4 point functions at tree level is given in the green box, and we worked out the experimental values of these two green functions C2 and C4, and we found them to be 1 and minus 2. These values at the tree level, if we remain at the tree level, gave us the value of m and lambda as 1 and 2 respectively. On that basis, we worked out the value of C6, that is the 6 point green function, and we found it to be 40. We thereafter increased the level of perturbation from 0 loop level, that is the tree level, to the 1 loop level for C6, and we found that if we use the existing values of m and lambda that we have obtained earlier, m equal to 1, lambda equal to 2, we get the value of C6 at the 1 loop level as 33.60. That is what we obtained. Then we went backwards, we worked out the formula for C2 and C4 also at 1 loop level, and we introduced corrections for the 1 loop for the first loop level, and we found on that basis, using C2 and C4 formula at the 1 loop level, we found MH1 to be 0.995 and lambda at the 1 loop level as 2.056. If we use these new values for working out the C6 at the 1 loop level, we find it to be 38.92. Now, the important things are that firstly, that this process shows how renormalization should be carried out. If you are going to work out C6 at 1 loop level, you must use the bare parameters in the action also worked out at 1 loop level. In other words, the green functions that have been used for working out the action parameters must also have a consistent or an equivalent level of accuracy, level of perturbation to the green functions that are being predicted. So, that is what renormalization mandates. The second interesting part is that when we use the action parameters at the tree level, we got the value of C6 at 1 loop level as 33.60, and when we use the expression for the action parameters at 1 loop level and worked out C6 also at 1 loop level, we got 38.92. Now, obviously, it is very clear very obvious from this point that the difference between the C6 values without renormalization is much more than the difference between the values at successive levels of perturbation worked out at after renormalization. So, that is important. Renormalization tends to make the values converge rather than diverge. So, that is a very important aspect that was formalized in the process of working out the theory of renormalization. Let us take another example, a slightly more involved example. We again in this case we use the phi 3 by 4 theory, and the values of the various green functions, connected green functions to first order in perturbation are given in your slide. C1, C2, C3, C4 and C5. Now, we assume that the experimental results, experiments were carried out, scattering experiments were carried out, and connected green functions C2, 3 and 4 experimental were measured and obtained, and these experimental values were used for calculating mu, lambda 3 and lambda 4 at the first level of perturbation, at the one loop level of perturbation, and let us assume that we get the experimental values as C 2 as h bar, C 3 as minus h square, and C 4 as 2 h cube. Now, using these experimental values and using the expressions for C 2, C 3 and C 4 at lowest level in h bar, what we get is mu is equal to 1, lambda 3 is equal to 1, lambda 4 is equal to 1. This is what we obtain from the equations that are there in your blue box, and we get the results that are there in your green box at the bottom of the slide. Now, what we do is if we use these results, and we work out the values of C 1, C 2 and so on at two loop level, what we get is the results that are shown in your slide, in this slide. In other words, using the one loop values, these are one loop values, the values given at the in the green box are one loop values, one loop perturbation values, and if we use these values and we work out the connected functions at two loop levels, we get these results. Now, it is very clear from these results that the values of C 2, C 3 and C 4 that is given on this slide do not coincide with the values that were observed experimentally. You can clearly see here C 2, C 3 and C 4 here on this slide, and C 2, C 3 and 4 here at the top of the slide, they do not coincide. So, what we do is we need to revert back to C 2, C 3 and C 4. We need to rework them at the two loop level. When we rework them at two loop level and then work out the values of mu, lambda 3 and lambda 4, the values that we get is given at the bottom of this slide. Let me repeat, and C 2, C 3 and C 4 values we had obtained at the one loop level, and those were the values that we saw here in the green box. These were the one loop values, but we then estimated, using these one loop values, we estimated the green functions at the two loop level, and we found that C 2, C 3 and C 4 do not coincide with the experimental results as is to be expected. Therefore, we revisited C 2, C 3 and C 4. We worked out this C 2, C 3 and C 4 at the two loop level. Using the revised working of C 2, C 3 and C 4 at the two loop level, we reworked the parameters at the two loop level, that is, we reworked mu, lambda 3 and sigma 4 at the two loop level, and then we used these expressions to work out C 1, C 2, C 3 and so on. And we find now that C 2, C 3 and C 4 do coincide with the experimental results. That is one part of the story. The second part of the story is that if you look at this, if you look at the relative values, the naive values that we use without renormalization and the values that we used with renormalization, you find that the differences are much less in the case of renormalization vis-a-vis the values that are worked out on the naive basis. So, that is an important this is an important topic. This of course would be carried on towards when we talk about field theory in Minkowski space, but fundament at the conceptual level, this is what renormalization is all about. We now talk about loop divergences. Now, what do we mean by loop divergences? Feynman diagrams for certain field theories or certain types of actions contain diagrams which take the form of loops. These loops arise from summation over internal degrees of freedom in these diagrams. When the summation is to be done over internal degrees of freedom, for example, internal momentum and the integration is to be done from 0 to infinity, the divergences may arise. Although in the case of zero dimensional field theory, the concept of loop divergences is redundant, because there is no concept of momentum as such, there is no concept of a metric, no concept of distance, and no concept of velocity, and therefore, there is no concept of momentum, and as a result of which loop divergences do not exist in zero dimensional field theory, but by way of illustrating the phenomenon, we introduce certain new features into our phi-4 theory. We introduced two new Feynman rules. We apply a factor of 1 plus C1 to every closed loop that contains precisely one vertex, and we apply a factor of 1 plus C2 to every closed loop that contains precisely two vertices. Loop with more vertices remain unaffected. So, these are two rules that we add to the existing repertoire of rules to externally introduce the concept of loop divergence in our phi-4 theory in zero dimensional space time, because a priori in zero dimensional space time loop divergences would not exist. And we will then later on we will make C1 and C2 approach infinity to explore the implications of loop divergences. Diagrammatically, in terms of Feynman diagrams, the two rules translate to this to what is shown in your figure. In this figure, if you have a loop with one vertex, that is the upper diagram, it translates to a loop and a dotted loop, where a dotted loop is C1 into the original loop. Similarly, if you have a loop with two vertices, it translates to a loop with two vertices and a dotted loop with two vertices. The dotted loop with two vertices is nothing but C2 into the original loop. Recall that in due course C1 and C2 would be made to approach infinity. Now, we will look at the Schwinger-Dyson equation. Having introduced the new Feynman rules to take cognizance of the possibility of loop divergences, we introduce the Schwinger-Dyson equations. Let us write down the set of Feynman diagrams and then write down the Schwinger-Dyson equation on the basis of those diagrams. With the introduction of dotted loops, the Feynman diagrams, the red colored boxes figures with red colored boxes are the new additions to the Feynman diagrams, and these are mandated by the introduction of dotted loops. Let us look at the definition of these red colored boxes. The red colored boxes with two lines represent single vertex with a dotted loop in this form, which is given here. This is nothing but C1 into the original loop. This is C1 C2 in original loop. Then we will have C1 C2 square into the original, and so on. And this diagram is the extra diagram here. And if we have a box with four vertices, this is equal to the two vertices dotted diagram, and then the two vertices dotted diagram in parallel, and then 3 and so on. So, this is how we define the boxes that are shown here, and let us call this A1 and let us call this A2. The upper box is the upper diagram. On the left hand side, let us call it A1, the lower diagram on the left hand side, let us call it A2. Then making use of this set of Feynman diagrams, we can write down the Schwinger-Dyson equations, including these loops, in the form of this expression. This is the Schwinger-Dyson equation for the phi-4 theory, including the various loops, and it can be written simplified and written in the form which is given in the lower equation, the bottom equation here. The upper equation corresponds to a diagram wise evaluation of each diagram. For example, the first diagram here is evaluated as j upon mu. The second diagram, if you note, is evaluated as minus a1 upon mu into phi. This part is phi, this loop is phi, the box here is minus a1 and we have one line. So, we have 1 upon mu. So, 1 upon mu a1 into phi, and that is the way the evaluation is done for all the other diagrams here. And this whole equation can be written in a simplified manner in the second equation that is given at the bottom of your slide. For the phi 3-4 theory, the equation becomes a little bit more involved. It takes the form that is given on this slide. Now, if you look at the action that corresponds to the Feynman diagrams that include the dotted diagrams, that in other words that include the red boxes, then the dotted or renormalized action takes the form of the bottom equation, the equation that is given below. This was the original equation. The upper equation was the original equation and the bottom equation is the renormalized equation action, renormalized action. The upper action is the original action, as you can very well see, and the bottom action is the renormalized action, which gives rise to this particular Schwinger-Dyson equation, the bottom Schwinger-Dyson equation. Now, it is a very interesting observation here. In this action, if you look at it, the bare parameters of the action, that is mu and lambda 4, these were the bare parameters, as you can see from the upper expression for the action. These were the original parameters. They do not appear alone anywhere in the action, because they appear in the action itself together with a1, mu appears with a1 and lambda 4 appears with 3a2. So, it follows as a corollary that wherever whether it be an experimental measurement or it be a theoretical computation of any level or any computation of green functions or connected green function or any other parameter or any other attribute of the theory, these two expressions will appear as one unit, as a complete unit. Mu will always appear with a1 and lambda 4 will always appear with 3a2 if we take account of the loop divergences represented by the dotted diagrams. Now, there is another fallout of this. The fallout is that if now C1 and C2 are allowed to approach infinity or allowed to move infinity representing divergences, then obviously A1 and A2 approach infinity, A1 and A2 also tend to infinity. So, in some sense it would trigger a reaction that the action becomes unbounded and therefore, the theory fails. But what recovers the theory or what saves the theory is the fact that we can have mu also, the bare parameters also infinite, and as such the infinities could very well cancel each other, and if the infinities cancel each other, then we are left with finite quantities, and therefore, the action becomes finite at every level, and all computations arising from the action. In fact, the theory itself becomes a finite and a viable theory. So, in a sense this enables us the fact that mu and a1, lambda 4 and 3a2 occur in pairs invariably, essentially enables us to do a kind of renormalization to get out of a situation where the loops A1 and A2, the collection of loops represented by A1 and A2 show divergent behavior. Right. Now, let us explore the concept of renormalization a bit further. Now, we look at the issue of scale dependence. when I talk about scale dependence, I am essentially talking about the various factors that influence the measurement, experimental measurement of the green functions or the connected green functions. You see, the fundamental thing is that these quantities are usually measured by scattering experiments. Now, scattering experiments or the outcome of scattering experiments really depends on the energy scales at which the experimental apparatus is able to operate, and therefore, it becomes relevant to explore the impact of such factors as the level as the energies involved in the scattering experiments on the measured quantities of attributes or parameters of the theory. So, that is the next exercise. Right. So, let V be the bare parameter as it occurs in the action. V is the original parameter that occurs in the action. We are now, for the moment, we are confining ourselves to a theory with only one parameter. For example, it could be a massless quarks and gluons theory with their interaction. So, there is only one parameter here, there is no mass term, and there is only one parameter that is involved in the action, that we call V. V is the bare parameter, W is the renormalized parameter which is extracted from the experiment. Repeat, V is the bare parameter as it occurs in the action, and W is the renormalized parameter extracted from the experiments. Now, the renormalized parameter, a renormalized coupling or the renormalized parameter W would be a function of not only the original parameter, the bare parameter V, but also the scale of energy or such similar factors that we are clubbing together as a scale. So, it would be a function number 1 of V, which is the bare parameter, the true parameter of the theory, and number 2 S, the scale of operation of the apparatus by which this determination is taking place. So, we can write W as a function of S and V. Now, we need this relation to be invertible because we want to be able to determine the bare parameter out of the renormalized outcomes or the renormalized computations or the renormalized observations, and therefore, we must have V is equal to G S and G of S and W, which enables us, using 1 and 2, we can simply write equation number 3. Now, by differentiating these two expressions, equation number 1 and equation number 2, we can arrive at these two fundamental results. F1 G1 is equal to 1, F0 plus F1 G0 is equal to 0, where the suffix 0 relates to differentiating with respect to S, and 1 represents differentiation with respect to the other parameter, other independent variable that the F or G depend on. For example, F depends on two parameters S and V. So, when I write F1, it is the derivative of F with respect to V, and when I write F0, it is the derivative of F with respect to S. Now, we can choose the scale such that the bare and renormalized couplings coincide when the scale is 0. In other words, we can define our scale in such a way, define S in such a way that at S equal to 0, the renormalized and the renormalized value V and the bare value renormalized value W, I am sorry, renormalized value W and the bare value V coincide. Let me repeat, we can choose the S equal to 0 at that point, at that scale at which the bare value or the bare parameter V equals the renormalized parameter or the value of the parameter through renormalization, that is W. So, I can write f 0 of V is equal to V, because remember f 0 f s of V was equal to W. If you recall, f s of V was equal to W, we are defining the 0 of S such a way that at S equal to 0, W is equal to V. Now, we investigate the relationship between the renormalized parameters, that is W, and the various scales, that is the energy scales or such other scales. So, under an infinitesimal change of scales, the renormalized coupling will change as ds dw by ds. dw by ds is given by this expression. W is nothing but f s v, and that is nothing but this expression where I have substituted v equal to g s or w. So, interestingly, if you look at this expression, the first and third equations, the first and third terms, there is no mention of the parameter v at all here. There is absolutely no mention of the parameter v. Recall that the parameter v could also take infinite values in view of the concept of renormalization that I had explained just a few minutes back. Now, however, the scale itself can become infinite, and therefore, this expression dw upon ds can have a meaningful or a sensible value or a logical value only if the derivative with respect to s or this expression dw by ds is independent of s, because s can take values up to infinity. So, that being the case, we must require that the derivative of w with respect to s must be independent of s. Now, if you simplify this expression, what we get is f 01 g 0 plus f 00 is equal to 0. There are quite obvious straightforward steps in simplification, nothing else, simply taking the total derivative as expanding the total derivative, that is it, and we get f 01 g 0 f 00. Recall f 00 is the second derivative of f with respect to s, f 01 is the derivative of f with respect to s and with respect to v, and g 0 is the derivative of g with respect to s. Hence, we have two equations, f 01 g 0 plus f 00 equal to 0 and f 0 plus f 1 g 0 equal to 0. Using these two equations, for substituting for g 0 from the second equation in equation 1, I get the equation in the blue box. If I divide throughout by f 1, I can write this equation in the form that is given at the bottom of your slide. The first equation at the bottom of your slide, which simplifies to the second equation, that is the equation given in the green box at the bottom of your slide. Now, from this expression, we find from this expression, if you look at it carefully, del by d by ds, df by ds, df by dv is equal to 0. That means what? That means df by ds is equal to some constant into df by dv, some df by ds is equal to some function of v into df by dv. df by ds is equal to some function of v into df by dv. So, I can write it as this way: df by ds is equal to beta of v is some function of v into dv by df by dv. By separation of variables, we can solve this equation, and we find that f s v can be written in the form of f script s plus h v, where h v is a new function which is obtained by this expression, integral of dv upon beta v. Now, recall w is equal to v if s is equal to 0 by the definition of S is, by the definition of our scale, we have defined our scale in such a way that at S is equal to 0, W is equal to V. Therefore, what happens? V is equal to W is equal to F 0 V. We have already shown that is equal to F H of V, because S is equal to 0 here. If I put H equal to 0, I get this F 0 V, which is nothing but V, which is nothing but W. So, V is equal to W is equal to F 0 V is equal to F script S is 0. So, F script H V, and from this what do I infer? I infer from V is equal to F H V, that F and H are inverses of each other, and F and H are inverses of each other, and if H and F and H are inverses of each other, we automatically have W is equal to F of H V, and W, but W is also equal to F S V, that is equal to F S plus H V. Now, from these two equations, W is equal to F script H V, and W is equal to F script S plus H V. I am sorry. W is equal to F script H W, and W is equal to F script S plus H V. That implies that H W must be equal to S plus H V. So, now we take the derivative with respect to S, we get d by ds of W, d by ds of W is equal to d by ds of F S V, that is equal to F S plus H V, that is equal to F dash F script dash S plus H V, that is equal to F script dash H W, that is equal to 1 upon H dash W. This is quite obvious, because W is nothing but S plus H V, it is here. Just a minute. Yes, here H W is equal to S plus H V. So, H W is nothing but S plus H V. So, I have put this here, and then I have this is nothing but F S V is equal to F script S plus H V, F H V is equal to F script S plus H V. The derivative takes the derivative here, and then we have S plus H V is equal to H W. So, this becomes here, and this is equal to 1 upon H dash W. Why is this shown in the expression on the red box, that F dash H W H dash W is equal to 1, that is why F dash H W is equal to 1 upon H dash W. So, we finally arrived at the scale dependence d W by d S is equal to 1 upon H dash W, and but H V is equal to integral d V upon beta V, and therefore, H dash W is nothing but beta W. When you differentiate H V is equal to this expression, you differentiate and put V equal to W, what we get is beta W. So, d by ds is equal to W S is equal d by ds W S is equal to beta W. So, all reference to the bare coupling has been removed. Number 1, the renormalized coupling has a definite predictable dependence on an energy scale of the measuring experiment, that is given by beta W. The equation d by ds W S is equal to beta W is called the renormalization group equation, and the group parameter is the shift in the scale. The group parameter or the group operation is the shift in the scale. So, I repeat, the equation d by ds W S is equal to beta W is called the renormalization group equation, and the group operation is the shift in the scale. So, this is important, and beta W is the beta function which governs the running of the parameter, that is the behavior under changes of the energy scale. Thank you.